Hey everyone, welcome back to the channel. This is the second video in my series on the Zindi Lelapa AI Buzuzu-Mavi challenge, where we're working to make African language models leaner and smarter, with a special focus on Swahili and Hausa. If you caught my first video, you'll remember we covered how to use Q-LoRa supervised fine-tuning to adapt the Incuba LLM model specifically for machine translation tasks. Today, we're taking things a step further by tackling a critical challenge in multitask fine-tuning. I discovered an interesting problem when trying to train a single model to handle multiple tasks at once: sentiment analysis, machine translation, and true or false question answering. The model was performing well on some tasks, but completely failing on others. I'm going to show you exactly why this happens and walk you through a simple but powerful fix that dramatically improved performance. This solution actually helped me secure a top 5 position on the leaderboard, so it's definitely worth understanding if you're working with multitask learning, especially in low-resource language settings. Let's dive right in. The core issue we're dealing with today is pretty straightforward, but easy to miss. When we're fine-tuning a language model on multiple tasks simultaneously, the default behavior of most training frameworks is to optimize for loss per token, not per sample or per task. Why does this matter? Well, imagine you have two tasks, one where the model needs to generate a single word as output, like a sentiment classification task where it just needs to say positive or negative, and another task where it needs to generate a full paragraph translation. If your loss function treats each token equally, the translation task will dominate the training process, simply because it has more tokens per example. This means your model will prioritize getting good at translation while potentially ignoring the sentiment task almost entirely. This is exactly what was happening in my work with African language tasks, and today I'll show you how a simple technique to balance these tasks made a huge difference. Let me walk you through the notebook so you can see this in action. I'm working with 3 different tasks across multiple African languages. 1. A sentiment analysis task, where the model needs to classify text as positive, negative, or neutral. 2. A machine translation, MT, task between English and various African languages. 3. An XNLI task, which is a true or false question answering task. First, we load our datasets and take a quick look at what we're working with. As you can see in the code, we've got a combined dataset with examples from all 3 tasks. Each example has an instruction, input text, and a target output. What's immediately apparent when we analyze these datasets is the massive imbalance in output lengths. Let's check out the analysis. The sentiment task outputs are just a single word, things like kayakiawa, positive, or korao, negative in Hausa language. That's an average of just 1 token per output. The MT task, on the other hand, has outputs averaging around 11.8 tokens, with some examples having up to 62 tokens. And the XNLI task outputs are also very short, often just a single digit representing the classification. So already we can see the problem. The MT task has outputs that are more than 10 times longer than the sentiment or XNLI tasks. This means that during training, the MT task will have roughly 10 times more influence on the loss function and gradient updates. So what's the fix? Actually, it's beautifully simple. We just need to balance the contribution of each task to the loss function by making their output lengths more comparable. The approach I took was to repeat the shorter outputs multiple times. For example, instead of just outputting kayakiawa for a positive sentiment, we output kayakiawa kayakiawa kayakiawa, repeated enough times to roughly match the average length of the MT task outputs. This might seem a bit hacky at first, but it's addressing a fundamental issue in how the loss is calculated. By ensuring all tasks have similar output lengths, we're essentially giving each task equal weight in the training process. In the notebook, I used a repetition factor of 11, which brings the average length of sentiment and XNLI outputs up to roughly match the MT task. Let's look at the function I created to do this balancing. The implementation is straightforward. Here's the function balance target lengths. We create a copy of our data frame. Then for each task that's not our reference task, in this case, MT is the reference since it has the longest outputs, we apply a repetition factor to make the outputs longer. You can see the effect of this when we display examples before and after balancing. The sentiment task output goes from just kayakiawa to kayakiawa repeated 11 times. Same for the XNLI task, where a simple 0 becomes 11 zeros. We can visualize the impact of this balancing with a simple bar chart that shows the average output length for each task before and after our fix. Before balancing, the MT task completely dominated. After balancing, all tasks have comparable output lengths. Now let's train two versions of our model to see the difference. First, we set up our model using QLoRa, which stands for Quantized Low-Rank Adaptation. This is a really efficient fine-tuning technique that lets us fine-tune large language models with minimal GPU memory. I'm using the Lelapa LLM model, which is specialized for African languages. For our first experiment, we train with the unbalanced dataset, where MT outputs are much longer than sentiment and XNLI outputs. We use the SFT trainer from the TRL library, which handles the formatting of our prompts and responses. Then, for our second experiment, we use the identical setup, but train with our balanced dataset. When we look at the training losses, there's already a notable difference. The unbalanced training has a loss of 4.53, while the balanced training has a much lower loss of 1.99. This suggests our balanced approach is learning more effectively overall. But the real test comes when we look at the inference results on our test set. The difference is dramatic. For the unbalanced model, when we look at its performance on the sentiment task, it almost always predicts class 0, regardless of the actual sentiment. Out of the sentiment test examples, 295 are classified as class 0, 4 as class 2, and just 1 as class 1. This is basically a broken classifier that's defaulting to a single class. Now let's check the balanced model. With our fix applied, the sentiment predictions are much more varied and realistic. 57 examples as class 0, 150 as class 1, and 93 as class 2. This is a massive improvement. The model is now actually learning to distinguish between different sentiment classes. We see similar improvements for the XNLI task too. The balanced model shows a much more reasonable distribution of predictions across the different classes. When we look at the actual leaderboard scores, the difference is striking. The unbalanced model only achieved a score of 0.19, while our balanced approach reached 0.29, representing a more than 50% improvement that helped secure a top 5 position. This clearly demonstrates the issue. Without balancing the output lengths, the model essentially ignores the tasks with shorter outputs and focuses almost entirely on optimizing for the task with longer outputs. So what have we learned here? The key takeaway is that when fine-tuning language models on multiple tasks simultaneously, we need to be mindful of the different output lengths across tasks. If one task has significantly longer outputs than others, it will dominate the training process, potentially leaving the model incapable of performing well on tasks with shorter outputs. The simple fix of repeating shorter outputs to balance their lengths makes a dramatic difference in model performance across all tasks. Instead of excelling at one task and failing at others, our model now performs reasonably well across all tasks. This technique is especially valuable when working with low-resource settings, where we often need to make the most of limited data by combining multiple tasks during training. In a broader sense, this highlights the importance of understanding the internals of our training process, rather than just treating models as black boxes. Sometimes, seemingly small adjustments to how we prepare our data can have profound effects on model performance. I hope you found this walkthrough helpful. As I mentioned, This approach secured a top 5 position on the Zindi Lelapa AI Buzuzu-Mavi Challenge leaderboard, so it's not just theoretical, it really works in practice. If you're participating in the challenge or working on any multitask fine-tuning project, especially with African languages or other low-resource settings, definitely give this balancing technique a try. It could make a huge difference in your results. If you enjoyed this video and want more practical tips for the Lelapa AI Challenge or language model fine-tuning in general, hit that like button and subscribe to the channel. Drop a comment if you have questions or other techniques you found helpful for multitask learning with African languages. In the next video of this series, I'll be exploring another key aspect of the challenge, so stay tuned for that. Until then, happy modeling, and I'll see you in the next one.